Okay, we want to continue developing the equilibrium solution to the Liouville equation. And to begin with, we need to discuss three conditions on the function fn in general. And the first condition is the classical definition of a contraction. If we integrate Fn over all momentum space, then we should get simply the configurational function, and this is called a contraction. And we also recall that we have an indistinguishable system of particles, and this particular function, if we integrate it all over all configurational space in momentum space, we end up with n factorial, where n is the total number of particles or molecules in the system. So from these top two relations, then we easily see that if we integrate the configurational part over all of configurational space, then we obtain n factorial. In terms of our separable solution, integrating the function h sub n over all momentum space would give us 1. So these will be called the normalization conditions Okay, the second condition is that there should be no net or average momentum in the system at equilibrium. So if we look at then the average momentum of any kth molecule in the system, and we formulate our average in the usual sense, and we need to normalize over the momentum space, the result of all this should be 0 at equilibrium. And we mentioned that that wouldn't be true for a system that was not in the equilibrium state. We might expect that there would be some average flow, some average momentum in the system. In terms of our separable solution then, we can write this condition as an average over the Hn and this is pk equal to 0. Now the third condition on Fn is associated with the classical definition of temperature in the system. So now we're going to look at the average kinetic energy in the system. The average kinetic energy of any molecule would be taken as the pk squared over 2m, which is the kinetic energy itself, and then averaged over F sub n. And again, we need to normalize this. And so the average kinetic energy of any molecule, according to the classical definition of temperature, should be equal to 3/2 kT, where K is Boltzmann's constant, and T is absolute temperature. So you can see that if the average kinetic energy of a molecule in the system was 0, then that would correspond to a temperature of 0. In terms of our separable solution, then the definition of temperature gives us this expression, now involving the function h sub n. And note that the kinetic energy, pk squared, could be written in component form as pkx squared plus pky squared plus pkz squared. And for an isotropic system, we wouldn't expect any difference between any of these three contributions. Therefore, we can state that for any of those contributions, we could use the subscript L now. Each of those integrations should result in 1/2 kT contribution to the total average kinetic energy over the three components. Okay, let's return now to our separable solution in the momentum space part, which we obtained in the previous lecture. And we're going to rewrite this equation as follows. So we're shifting subscripts from KL, where K runs from 1 to N and L is 1, 2, or 3, to a new subscript J, where J now will run from 1 to 3 N. So for example, J equal to 4 would correspond to the second particle, K equal to 2, and L equal to 1. So that makes it a little more compact. We've also introduced a lambda prime defined as lambda divided by the particle mass m. Now we integrate this equation with respect to Pj to obtain first an arbitrary function of all the remaining momentum coordinates, which we could write as 3n minus j, and the integration over p sub j results in just a simple exponential where now again this first term is an arbitrary function of the remaining momentum variables. And again, note that J is going to run from 1 to 3n. So, since that solution holds for any j, the general solution then for h sub n would be the product of all the exponentials over any j. So this is the only way that the function can be satisfied is if the total solution or the general solution is a product of all the exponentials. And here now d is a arbitrary constant and is a true constant and not a function.